Hey everybody, this is Dr. Jacobs. This week we're going to be learning about the one sample z-test. Let's go ahead and get started. This week there are some unit learning objectives that I would like you to be able to do by the time we get to the end of this lecture. I'd like you to be able to determine when to use the one sample z-test and when to use the one sample t-test. We're actually going to learn how to calculate one of them. They're both actually pretty similar, but I do want you to be able to know when you need to use both of these. I also want you to be able to construct research and null hypotheses for one-tailed and two-tailed tests in both symbols and in words. I want you to be able to determine whether the data meets the assumptions for the one sample z-test. I want you to determine if there is a violation of an assumption for the one sample z-test and determine if it is robust to violation of that assumption. I want you to accurately calculate the one sample z-test. I want you to be able to find the correct critical value or values for the one sample z-test. I want you to accurately write and interpret the results for the one sample z-test. I want you to calculate the appropriate effect size after finding statistically significant results from one sample z-test. Now let's go ahead and get started. So step one, you're going to notice these are the same steps that we learned last week during the hypothesis testing steps lecture. Each week from now on, we will keep following these same steps over and over again, but we are going to use them with relation to whatever statistical analysis that we're going to learn. So this week we're learning the one sample z-test is the analysis, and we will take it through all of the hypothesis testing steps that we've done so far. So one really good strategy would be to practice and memorize what our hypothesis testing steps are in order, because we're going to use that same framework over and over and over again. That way you have it and it'll be a lot easier for you to do. So step one, we're going to determine which statistical analysis to use. So far, we've not had to do that yet. So this will be the first week where we'll learn the one sample z-test. Next week, we'll learn one of the t-tests. And what you should do for each lecture now is, just like we have a symbol sheet that lists all of our symbols that we've learned so far, you'll want to create a sheet that has all the statistical analysis that we're learning for inferential statistics. So this week you would write one sample z-test, and then when we get done learning what a one sample z-test is and when we'll use it, you'll want to write that there too, because if you remember back to our syllabus, or back in the very beginning of the semester, one of the big things that I wanted you all to get from this class is to be able to know when to use which analysis. And so if that's super important to me, then that will probably be something that will be tested over. Okay? So step one, determine the statistical analysis. There are certain questions that you can ask yourself to determine which analysis that you want to use. First, we got to figure out, okay, what's our goal for whatever analysis that we're doing? So the goal for the one sample z-test is to see if there's a significant difference between the sample mean and a population mean. Okay, so second, if we're looking for significant differences like we are with the one sample z-test, our dependent variable must be on a scale. So if we remember back from chapter 1, a dependent variable is the thing that we're measuring in our study. And then if we remember when I say a scale, what do I mean? We said measure or data that falls on an interval or ratio level of measurement with correct. All right, so in order to run a one sample z-test, our dependent variable has to be on an interval or ratio level of measurement. If you're still struggling with levels of measurement, please feel free to come into office hours or to send me some questions over email. Okay, so third, this one's a little bit tricky, but we always want to know how many samples are we testing. So with the one sample z-test, it's tricky because we're comparing one sample mean to a population mean. And that's actually not something that we'll do very frequently. In fact, you do this with the one sample z-test. You also do it with the one sample t-test. But this is one of the very few times we're actually doing something like this. Okay, so that just means that we are testing one sample. And some people are like, it's the one sample z-test. How many samples are we testing? Well, if you look at the name, it just says one sample. It's not a trick, but it can be a little confusing since we're comparing two different means. Again, so students sometimes get confused about this because we're comparing the one sample mean to the overall population mean. All right, so the one sample z-test, this is what you're going to want to put in that handy dandy statistical analysis sheet that you're going to start building this week. So we do a one sample z-test. We use this to compare the mean of one sample to the mean of an entire population when we know the population's standard deviation. All right, so again, a one sample z-test is used to compare the mean of one sample to the mean of an entire population when we know the population's standard deviation. So side note, there's another analysis that's kind of similar to the one sample z-test, and it's called the one sample t-test. We're not going to learn to calculate both of these. I will talk about it here, and you should know when to use it, but I won't make you go through and calculate the one sample t-test with formula and everything. So again, although we won't do the one sample t-test right now, you should know when to use it. So we use a one sample t-test when we want to compare the mean of one sample to the mean of the whole population, and we do not know the population standard deviation. So we should put this onto that statistical analysis sheet that you're building too, because I will want you to be able to tell me, hey, we do a one sample z-test when we're comparing one sample mean to a population mean, and we know the population standard deviation. And then I could also ask you a question about this one. If we don't know the population standard deviation and we want to compare one sample mean to an overall population mean, which statistical analysis we use, and you would tell me that it's the one sample t-test. All right, so that brings us on to step 2 of the hypothesis testing steps. And in step 2, we write our hypotheses in both symbols and in bolds. So when we write our hypotheses, we can write our research and null hypotheses directionally or non-directionally. Okay, so when we're doing this step, that's the very first thing that we need to do. We need to determine, are we going to write them directionally or non-directionally? If we write our research hypothesis non-directionally, we also write our null hypothesis non-directionally. If we write our research hypothesis directionally, then we also have to do the same thing to our null hypothesis. And that is because our research and null hypothesis cover every potential answer to whatever our research question is. All right, so writing non-directional hypotheses, you only write them directionally or non-directionally. You do not do both of these things. And sometimes students get a little bit confused about that, but you only write them one of these ways. So if we're going to write our hypotheses, both of them are research and null hypothesis, non-directionally, there's a certain way that we do this, and you'll become familiar with this format because we'll be doing this over and over again as well. All right, so when we write our research hypothesis non-direction, we're first going to want to write the symbol for research hypothesis. So our symbol for research hypothesis, if you remember from the last unit, is capital H sub 1. If this is not on your symbol sheet, go ahead and make sure that is there now. So after we write H sub 1, we'll then put a colon next to it to let people know that we're getting ready to tell them the research hypothesis. So if you remember back to our description of the one sample z-test, what are we comparing? If you said that we're comparing the sample mean with the population mean, you're absolutely correct. Okay, so with non-directional hypotheses, we refrain from saying which one we think would be bigger, right? We don't want to say the sample mean will be bigger or the population mean will be bigger. We're just saying that we think that they're not the same. So here, with non-directional research hypothesis, we say there are significant differences, but we refrain from making a guess about the direction of those differences. All right, so how would you write a research hypothesis for non-directionally for one sample z-test in symbols? So we have that H sub 1 to indicate that we have a research hypothesis. We put a colon then to say, hey, the research hypothesis is coming. Then we have our symbol for sample mean, which we remember is X bar. Then we put the does not equal symbol to say that it does not equal, and we put mu, which is our symbol for population mean. So we remember we learned these symbols back when we were doing measures of central tendency back in week 2, and now they're coming back to haunt us a little bit, which is why I kept pounding, hey, we really need to memorize these symbols. And if we look at the hypothesis and symbols, it makes sense what we're doing because we're saying, hey, we're comparing a sample mean to a population mean, and we don't think they're equal to one another. And so if we go through and we just read that, we see that the hypothesis is actually telling us what we're testing with this analysis. So then we will take, I always write my hypotheses and symbols first because that's actually the easier way to do it for me anyway. And when we're doing one sample z-test, if we're writing them non-directionally like this is always what your research hypothesis will look like in symbols for one sample z-test. So then we want to translate the symbols to fit whatever our research study is, okay? So I have kind of a template that you can use. Template doesn't mean that you will write these exact words every time. What template means is you'll take this and you'll adapt it to whatever study that you're conducting, right? So the template for research hypothesis written non-directionally for the one sample z-test looks like the following. You'd write research hypothesis to identify which hypothesis you're indicating, put a colon to say here it comes, and then we put the sample mean is significantly different from the population mean. So what you can do is take this template that I've given you here in the PowerPoint, and you can adapt it into whatever study you're doing by inserting what your dependent variable is that you're examining. All right, so then continuing to write our non-directional hypotheses. If we've written our research hypothesis, we also need to write our null hypothesis non-directional. And so similarly, we'll write our symbol for the null hypothesis. If we remember back from last unit, our symbol for null hypothesis is capital H sub 0, right? Because the 0 means none or null. So we have H sub 0. Then we're going to put a colon and let people know that the null hypothesis is getting ready to come. And the null hypothesis is going to be the exact and complete opposite of the research hypothesis. So what would that be? Before we move forward in our lecture, what would it be? So if we see here, how would we write our null hypothesis non-direction for the one sample z-test? We would have H sub 0, then a colon. We have X bar, which means sample mean. And instead of the does not equal symbol, we have the equal symbol. And then we have mu, which is our population mean symbol. So we see here, that is the complete opposite. In our last one, we said they do not equal one another. And the null hypothesis, we say they do equal one another. And we also have a template for this as well. So our template for the null hypothesis, written non-directionally for one sample z-test, is null hypothesis. We have to identify which one we're doing. Put a colon to say this is the null hypothesis. And we say the sample mean is not significantly different from the population mean. So final notes on non-directional hypotheses for the one sample z-test. When we write non-directional hypotheses, we're conducting something called a two-tailed test. This means that when we move on later and find our critical values, that we will have two critical values. The critical value will be the same number, but one will be positive and the other one will be negative. Right? So we will, when we're doing these inference of statistics, we're always going to draw out some sort of normal curve. And so when we're looking at a two-tailed test, because we run two-tailed tests when we wrote our hypotheses non-direction, we see that we have two tails on our normal curve here. We have one that's on the negative side and one that's on the positive side. And we will learn more about what these different areas are, but we have two decisions that we can make through the hypothesis testing steps. Either we can retain our null hypothesis or we can reject our null hypothesis. And that will be all based on what our critical values and our test statistic are later on. All right, so if we choose to write our hypotheses directionally, it'll be a slightly different, but pretty similar. So I always start off with writing the research hypothesis first, because that is the hypothesis as the researchers that we typically want to be the accurate explanation for what's going on with our data set. So when we're writing our research hypothesis, the very first thing you're going to do is write them in symbols, because that's the easier method. We're going to write our symbol for research hypothesis, which is what? If you said capital H sub 1, you're correct. After that, then what are we going to do? If we said put a colon, that is exactly what we do next, because we want people to know that we're getting ready to tell them the research hypothesis. So again, what are we comparing with the one sample z-test? We said we're comparing sample mean with population mean. You're absolutely correct. So the thing that's different when writing directional hypotheses in comparison to non-directional hypotheses is that we typically have an idea of which one's going to be bigger, the sample mean or the population mean. So when we're writing our research hypotheses directionally, we identify whether we think the sample mean is significantly greater than or significantly smaller than the population mean. Okay. So how would you write a research hypothesis directionally for one sample z-test and symbols if you think the sample mean will be significantly greater than the population mean? If you said h sub 1 colon x bar is greater than mu, you're correct. So then we would take that and we translate the symbols to fit our particular research study. One way to do this is to take this template that I'm about to give you and then adapt it for the specific study that you are conducting. So you will want to make sure that you're saving all of these PowerPoints and Google Slides that I have for this class, because especially if you're going on to the research methods class next semester, or if you're planning on going on into graduate school, it's very likely that you'll need to use these again. All right, so if we're going to write these into words, the template that we have for this is we're going to write the words research hypothesis. Then we're going to say the sample mean is significantly greater than the population mean. Now, we didn't have to choose that, right? So with whatever study that we're doing, if we thought it was significantly less than, we could have done that. Right now, we're doing it this way, though, because it's easier for our brains to think in positive numbers than it is negative. And so I wanted to take you through a full example of how we would write our research hypotheses directionally in a way that our brains are going to understand it better. All right, so then we're going to move on to write our null hypothesis directionally, and we saw that we use the greater than symbol with our research hypothesis. So for our null hypothesis, it needs to cover every single option that is not covered by the sample mean is significantly greater than the population mean. Okay, so when we do this, we're going to write out our symbol for the null hypothesis, which is h sub 0. Then we're going to put a colon to let people know that we're telling them the null hypothesis. Again, the null hypothesis has to cover everything that our research hypothesis did not cover. So what would that be? So if you said, then that would be h sub 0 colon x bar is less than or equal to mu, you're correct. So remember, sometimes students struggle with this because they forget on the null hypothesis that it has to cover every single option that the research hypothesis didn't cover. So if we use the greater than symbol for the research hypothesis, then for the null hypothesis, we need the less than or equal to symbol. So then we also have a template that we can use to translate our symbols into words. So we have null hypothesis, colon, the sample mean is equal to or less than the population mean. So some final notes on directional hypotheses for one sample z-test. When we write directional hypotheses, we will conduct one-tailed tests. This means that we will have one critical value. The critical value will either be positive or it will be negative. So if the research hypothesis says the sample mean is significantly greater than the population mean, our critical value is going to be positive. However, if our research hypothesis says the sample mean is significantly smaller than the population mean, then our critical value will be negative. So if you see here, I have two drawings of a normal curve. If we, in our research hypothesis, say the sample mean is significantly larger than the population mean, we see that our critical value is going to be to the right of our normal curve, which means that we will have a positive critical value. However, if we said that in our research hypothesis that we thought the sample mean would be significantly smaller than the population mean, we see that our critical value will fall to the left of the center of our normal curve, making that value negative. So our next step in the hypothesis testing steps is to check for our assumptions. All right, so the assumption checking process, we check to see if our data set meets each of the assumptions for the statistical analysis that we're running. So the one sample z-test has different assumptions than we'll see with our one-way ANOVA whenever we get there, or our Pearson product normal correlation, or linear regression. So I will not make you memorize which assumptions go with which analysis, but you should be able to know how to check for each of these assumptions. Okay, so if our data set meets the assumption, then awesome, that is wonderful. You can check the rest of them. If we violate or we fail to meet an assumption, then we need to check whether our analysis is robust to the violation of the assumption given our data set. So if you remember, if you bake and you have a recipe, like say like you're making cupcakes and it calls for oil, if you don't have oil, sometimes you can go ahead and put applesauce in place of oil into the cupcakes, and the cupcakes will still turn out the same. They'll be slightly different, but not enough where your cupcakes would be ruined. And so it's kind of like that. If we don't have all the ingredients for our statistical analyses, sometimes there's other things that we can do instead and still run our analysis anyway. However, if we're making chocolate cupcakes and we don't have oil and we have a substitution of mustard, that probably wouldn't turn out with very good chocolate cupcakes, right? So we probably wouldn't do that. So just because there are some other situations where we can still run the analysis anyway, we have to make sure that it meets that other criteria to move forward with it. So again, this is just a fancy way of saying that we can run the analysis anyway, given certain circumstances. All right, so assumptions for the one sample z-test. Our dependent variable is measured on a scale. Remember, scale is data that is on an interval or ratio level of measurement. The dependent variable is free of outliers. So we learned about how to check for outliers earlier on. And so we will practice doing that. The population we took our sample from is normally distributed. We'll learn a little bit about that. And then our sample was randomly selected. And so we learned about the different types of sampling methods from the very first week, and we'll continue that here. All right, so the first assumption that we're going to check is that our dependent variable is measured on a scale. This means that our DV is on an interval or ratio level of measurement. So the one sample z-test is not robust to the violation of this assumption. What that means is that if our dependent variable is not measured on a scale, then we cannot run this analysis. So this is a deal breaker here. I know some people have deal breakers when they're dating people, right? That means if that person doesn't meet that characteristic, then you will not date them. That is what is for a one sample z-test. If we do not meet this assumption, then we cannot run this analysis. All right. So again, this means if our dependent variable is not on a scale, we cannot do this analysis. We cannot do the one sample z-test. This is because we cannot, if you remember back from week 2 when we were doing measures of central tendency, we cannot calculate the mean with data that's on a nominal or ordinal level of measurement. Okay. So our formula for the one sample z-test uses the mean for the sample and population along with the population standard deviation. And if we can't calculate a mean, we can't do that. Okay, our next assumption is that our data set is free of outliers. What was our definition of outlier again? So our definition of outlier is an extreme score. How do we determine if our data set has outliers? And we learned this back when we were learning about z-scores. So to do this, we calculate the z-score for each individual score of the dependent variable. So for every single x value that we have in our data set, we'll need to go and calculate the z-scores that we learned to calculate. If we have any z-score that equals 3.29, a negative 3.29 or below, or positive 3.29 or above, those are considered outliers. So if we have any outliers in our data set, we violate this assumption. However, the one sample z-test is robust to the violation of this assumption if we remove the outliers prior to running our analysis. So what this means is if we have a data set and we go through and we calculate all of the z-scores for each of our x values, if we see a z-score of 3.29 or bigger, or negative 3.29 or smaller, that's an outlier. We would, if we wanted to keep running this analysis, we would need to remove that entire data point, that entire x value out of our data set. And then we would need to write into our results section that we removed this number of participants because their data were outliers based off the plus or minus 3.29 z-score criterion. Okay, so the mean and outlier example. So if we have this data set that we see here, we have x, and then we have the x values. So we have 2, 4, 3, 2, and 100. If we have this data set and we need to determine if there were outliers, what would we do first? First, we'd have to find the mean, right, and the standard deviation so that we can calculate each score's z-score. So how do we find the mean? You're right, we take the summation of x and then we divide by the number of participants. So here we see that our mean is equal to 22.20. So after we find the mean, what is the next step to find the z-score? Our next step would be to find the standard deviation. So to do that, we need to find the deviation scores for each x value. So we know that the symbol for deviation score is capital D, and that equals x minus x bar, and we do that for each individual x value. So here we see if we wanted to find the deviation score for 2, we would take 2 minus 22.20, and that would get us a deviation score. So this is what we have here. You can see what our deviation scores are. To find the standard deviation, after we find our deviation scores, we know that we need to square each of our deviation scores. We know that if we add up all of our regular deviation scores in that second column there in our table, that they should equal 0. Sometimes when we round, however, it might be a little bit off, but that is definitely one way that you can double check to make sure that you are on the right path. All right, so after we square each of our deviation scores, what do we do next? We said we add up all of our square deviation scores. You're correct, and that's called our sum of squares. So we find our sum of squares by adding up all of the square deviation scores, remembering that our symbol for sum of squares is SS. And when we do that here, we see that equals 7,568.80. Then we put that information into the formula for standard deviation. So we know that standard deviation is equal to the square root of our sum of squares divided by our sample size minus 1. And then we just follow that out one by one, and we make sure that we write out each step. And when we do that, you see here that we can go ahead and move forward and start calculating our z-scores. Okay, so after you have your standard deviation, what's the next step to calculating the z-scores for each x? Well, you're going to plug that information into our z-score formula, which we remember is z equals. In the numerator, we have x minus x bar. But if we think back to what that means, that's just our deviation scores divided by our standard deviation. Right, so if we do that here, we determine if there's any outliers. We need to examine those z-scores for each x value. And we look to see if any value equals negative 3.29 or below, or positive 3.29 or higher. And for some reason, it's not popping up the way that I want it to. So let's go through here. I'm going to put something into my calculator real quick. So our standard deviation here is the square root of 1,892.20. And when we do that, we see that our standard deviation is approximately 43.50. So to do that, so for the x, we would take our deviation score, which we see is negative 20.20 divided by 43.50. So our first x value 2 has a z-score of negative 0.46. So that is not going to be an outlier. Our next one, we take our for our x value of 4, we'll take negative 18.20 divided by 43.50. We see that our z-score is negative 0.425, so negative 0.43. That's not an outlier. Our x of 3, we see that our deviation score is 19.20. Okay. We're going to divide that by 43.50, which is our standard deviation. And we see that that is a z-score of negative 0.44, which is still not an outlier. Our next one is negative 20.20 deviation score for x value of 2, which we've already done earlier, but I always like to go through and check each of these individually. So divide by 43.50, and here we see that that has a z-score of negative 0.46, but that is still not an outlier. So our last one that might be suspect a little bit is our x value of 100. We see that our deviation score is 77.80. We're going to divide that by 43.50. I believe is our standard deviation, which gave us a z-score of 1.79, which is also not an outlier. So here we see that we have 0 outliers in our data set. And so here's a second example of outliers. Here you'll see that I calculated z-scores for you already. So how many outliers are there in this data set? So just take a look through the data set here. You see here how many of these z-scores are 3.29 or higher, or negative 3.29 or lower. Don't write the answer in the comments or anything. Just think about this out loud. We're doing Dora the Explorer again. You see here we have one participant has a z-score of 3.38. That's participant number 8. So we have found one outlier in this data set. So if we wanted to use this data set for one sample z-test, we'd have to remove participant 8's data, that 10, which would give us only 12 participants in our study. And if you remove any of these outliers from your data set prior analysis, you need to indicate how many outliers you removed in the results section and why. Okay, so if we go through with that last data set and we look at what the mean looks like with the outlier and without, we see there's a significant difference between the mean of our data set with the outlier in it, which was 1.69, versus when we removed the outlier and found our mean, and that mean of that data set would be 1.00. You can see here, we have the 2 different data sets. One has an outlier and one does not. We never just remove data from our data set and not say anything. That's actually kind of considered unethical. And so make sure anytime that you do anything to your data, that's something that you write in your manuscript so people know what you did. And if they had your data set, they'd be able to replicate your results. So again, if this was your data set, you would need to remove the outlier from it before moving forward with the analysis. Note this will change your sample size because you'll be removing the data outlier for that participant or participants if there's more than one. Okay, so this next assumption is a little tricky. And with this third assumption, we're testing for one sample z-test, that the population we took our sample from is normally distributed. So here it's really tricky with the one sample z-test because with the one sample z-test, we're comparing one sample to the overall population. Almost never do we have an entire population with the data. And that's why sometimes I actually have never used the one sample z-test in the real world. I've only used it to teach about the hypothesis testing steps within stats class. It doesn't mean that you wouldn't do that. In fact, if people were wanting to see if one particular subgroup of a population had significantly different scores than another, like the population overall, you definitely use this analysis. So sometimes people will look at equity for different things by using the one sample z-test. It's just not something that I have used so far. Okay, so for this assumption, we're actually talking about the population we took our sample from rather than the overall population. Typically, we'll have access to the population we took our samples data from, or we wouldn't have to run the one sample z-test. We do have the data set for our sample though. Okay, so typically we'll use something called the Shapiro-Wilk test for normality to test for this assumption in our sample. For this, if our Shapiro-Wilk test for normality is statistically significant, then we violate this assumption. So whenever we do this, if I want you to use the Shapiro-Wilk test to test for normality, I will give you a p-value. If our p-value is less than 0.05, then we violate this assumption. However, if we violate this assumption, we can still run this analysis anyway, as long as our sample size is 30 or more. At a Shapiro test for normality, we use this to determine if our sample's distribution is significantly different from the normal distribution. What's a distribution again? This is how frequently each value occurs within a data set. If you remember earlier on, we used the histogram to be able to visualize what the distribution of our data set looks like. And the distribution of our data set occurs whether or not we display it visually. So if we want our sample to be normally distributed, do we want it to look significantly different than the normal distribution? No. If our sample's distribution is significantly different from the normal distribution, it is not normally distributed. And we want it to follow the normal curve shape to be able to run this analysis. So this means in order to meet the normality assumption, there must be no significant differences between our sample's distribution and the normal distribution. Okay. So in other words, if we are running, so this Shapiro-Wilk test is actually its own statistical analysis that you can take through the hypothesis testing steps. And if we did that and we wrote our hypotheses out, that would mean we'd want to retain the null hypothesis for the Shapiro-Wilk test for normality, which means the p-value for the Shapiro-Wilk test, we want it to be equal to or greater than 0.05. And this can be slightly tricky for people because this is exactly opposite of what we're going to want to find in step 6. Okay, so what should the p-value be for the Shapiro-Wilk test in order to meet the assumption? It should be greater than or equal to 0.05. That is the biggest thing that I hope you take from this. You don't necessarily have to understand what we mean by saying, is our distribution significantly different than the normal distribution? What you need to be able to do is look at the Shapiro-Wilk test p-value and know whether or not we met the assumption. So testing assumptions like the Shapiro-Wilk test for normality is one of the few times that we actually want to retain our null hypothesis. The test statistic for the Shapiro-Wilk test for normality is W, and we will actually see the same test statistic later on for a different assumption, but that's going to be for one of our more complicated analyses. Make sure, do not get this confused with the decision that we'll make in step 6 when we're making a decision about our research question. So here's an example. For testing for normality, you'll see here I have a data set. So if I want to know if biological males in the NBA are significantly taller than the overall population of biological males, I could take a sample of NBA players and compare that sample to the overall population of males. So I decided to use a convenient sample and use the Milwaukee Bucks. So to test the normality assumption, I would need to determine if the distribution of my sample was significantly different from the normal distribution. So for this data set, our p-value equals 0.839. So will we meet or violate the normality assumption for this data set? You would meet it. All you have to do is look at that p-value. So in the real world, you'll actually be using computer software to calculate all these values. And so SPSS is one of the predominant types of statistical software that you would use. And so to find this, you would go into SPSS, you would click Analyze, then you would go to Descriptive Statistics. Then you would go to Explore, ignore the sirens in the background. Then you would put your dependent variable into that dependent variable list. And then you would click Plots. you'll see there's a box that says normality plots with test. You'll make sure that you have that endorsed. And then it'll pop out some display here. You'll see it's labeled Shapiro-Wilks, where it says SIG period. That is your p-value. So you look at that sig value to see if it is 0.05 or larger, you meet the assumption. If it is less than 0.05, then you violate the assumption. So final notes on normality. If our p-value was 0.03 in the previous example, where our sample size equals 17, what would that mean with relation to the normality assumption? And this is something that I could ask you to do on a test, right? So although you're not doing math on tests, I could ask you if you met or violate the assumption, and if you violate the assumption, if the one sample z test is robust to the violation of this assumption. All right, so it would have meant that a sample's distribution was significantly different from the normal distribution, which is bad. We don't like that. So then we would have to see if our one sample z test was robust to the violation of this assumption. Yeah, because we violated it. And our one sample z test would not be robust to the violation of this assumption because our sample size was less than 30. What that means is if this happened, if our p-value is